Okay, so let's start. So in the last few classes, we've been looking at this Lagrange multiplier formalism to solve convex optimization problems, or generally constrained optimization problems. Right? So given an optimization problem in this particular form, uh, we first define the Lagrangian, and the Lagrangian is just a linear combination of the objective function and the functions that define the inequality and equality constraints. And then taking the supremum for every Lagrange multiplier, taking the infimum of the Lagrangian over all x in the domain gives us the Lagrange dual function. So corresponding to every primal optimization problem, we can define the so-called dual optimization problem, which corresponds to minimizing, which corresponds to maximizing the dual objective function g of lambda comma nu with respect to lambda greater than or equal to 0 and nu in Rm, right? And we saw that if strong duality holds, we saw that g of lambda comma nu always gives a lower bound on p star, the object that we are interested in. And so maximizing g of lambda comma nu gives us at least a lower bound on p star, but in many cases it actually gives us p star itself, because the maximum of or the solution to the dual optimization problem can give you p star. All right. And towards the end of last class, I said that there is a method, sort of an algorithm, if you will, to solving not just the primal optimization problem, but also the dual optimization problem in one go. So the way is, given the primal optimization problem, you first construct the Lagrangian, and then using the Lagrangian, you verify whether this problem satisfies, or a given set of points satisfies these KKT conditions. All right. If you are able to find some x star, lambda star and nu star that satisfies all of these KKT conditions, then you output that particular x star, lambda star and nu star. All right. So the KKT conditions are as follows. So firstly, we want all of the primal constraints to be satisfied. So these are the primal feasibility constraints, or the primal feasibility conditions. The dual must satisfy the dual feasibility conditions, that is lambda star should be greater than or equal to 0 component wise. It should be stationary, so the gradient of the Lagrangian with respect to x should be equal to 0 at x star, lambda star, nu star. But in addition, we also have this complementary slackness condition, that is for each corresponding to each inequality constraint, we want lambda I star times fi of x star to be equal to 0. Okay, so these put together, these are the KKT conditions. We'll sort of try to derive the KKT conditions. And we'll see that the KKT conditions are, in general, they're not sufficient. Okay, I'll state exactly what the requirements are. So in general, if the primal optimization problem if it satisfies strong duality, then the KKT conditions, they're only necessary. So the optimizer must satisfy the KKT conditions, but just because a point satisfies the KKT conditions does not imply that it is actually a solution. Okay, every solution must satisfy the KKT conditions, but just because a point satisfies the KKT conditions, it need not mean that it's a solution. It is the solution. Okay, this is for a general primal optimization problem, convex or non-convex, that satisfies strong duality. So strong duality implies that KKT conditions are only necessary. But if the problem is also convex, then the KKT conditions are sufficient. So strong duality means that KKT conditions are necessary, and convexity implies that conditions are sufficient. All right. So if you are given a convex optimization problem that satisfies strong duality, and you get a point that satisfies the KKT conditions, then you know that that is the solution. You don't need to look any further. Okay. But on the other hand, if you are given an optimization problem which is perhaps non-convex, and you get a point that satisfies the KKT conditions, it's not guaranteed that that is going to be the actual constraint minimum. But if you have a constraint minimum, it should satisfy the KKT conditions. Okay, hopefully that's clear. So before I even prove or derive the KKT conditions, let's see a few examples and see how the KKT conditions can make life easier. Now, in general, the KKT conditions may or may not help us to solve the constraint optimization problem easily. But there are many cases in which we can get either a closed form expression or get something that is almost a closed form expression. You just have to you can reduce it to maybe solving a system of linear equations or quadratic equations, and that's it. Okay. So effectively, the idea behind the KKT conditions is, from an optimization problem, you want to reduce this to a problem of solving for a system of equations, linear or non-linear. Okay, and if the system of equations is easy to solve, then you have an easy solution to the constrained optimization problem. Okay, so let's start with the following example. So a quadratic program, a general quadratic program with linear constraints. Basically, you want to minimize some x transpose ax plus b transpose x plus c, subject to the constraint that some matrix G times x is equal to some vector h. Now, note that we've seen some special cases of this when I talked about duality. For example, one problem was to minimize norm x square such that ax equal to b, or more generally you could minimize norm ax plus b the whole square such that gx equal to h. So all problems of this form, these are all special cases of this optimization problem that I have over here. Correct? So one requirement that I have here is that A is a symmetric positive definite matrix. So it's a D by D positive definite matrix. So as always, the first step is always to construct the Lagrangian. Let's write down what the Lagrangian looks like. So it is L of x. I have only equality constraints in this case. How many equality constraints do I have? Yeah? Yeah, so depending on what the number of rows of G is, or the length of H, let's say that G is A is a symmetric positive definite matrix. So generally when I say positive definite, it means that A is symmetric. So G is, say, an n by D matrix. I don't have any inequality constraints, only equality constraints. So the dual optimization problem is in fact going to be an unconstrained maximization problem because I don't have the lambdas. Right? So this can be written as x transpose ax plus b transpose x plus c plus, again, I can, instead of writing it out as a summation, I can represent the linear combination of the Lagrange multipliers with the equality constraints as just one inner product between nu and gx minus h. Okay, so hopefully it's okay up to this particular point. Great. So now let's list out all of the KKT conditions. So I have the primal feasibility constraints. The primal feasibility constraints they just say that gx should be equal to h. Let's make note of that. I don't have any other primal feasibility constraints. What about dual feasibility? I don't have any dual feasibility constraints because I don't have the lambda vector. It's purely a function of nu, so no constraints on nu. Third is stationarity. So the gradient of the Lagrangian with respect to x should be equal to 0. what is the gradient of this with respect to x? I'm sorry. Yeah, 2ax. Again, A is a symmetric positive definite matrix, so A plus A transpose is the same as 2A. So 2ax plus B. Yeah. Be careful with the dimensions. G transpose gamma. I'm sorry. G transpose. Yeah. I'm sorry.
No, with respect to the dimension, since A is square, you're okay so far.
Correct. I'm okay so far. I mean, the first part was okay, but someone said gamma transpose G, which is not right. So it's G transpose gamma. That's it. This should be equal to 0, right? Or 2ax plus G transpose gamma. This is equal to minus B. And I don't have any complementary slackness conditions because there is no lambda. Okay. Maybe if it helps, perhaps I can write down all the KKT conditions on one side. Hope this is visible. Okay, so right now it's not clear how I can simplify this any further, but if I stare at everything I have for a while, then essentially I already have a solution. Let me just collect the primal feasibility constraints and the stationarity constraints as one big system of linear equations. Right, so I have primal feasibility says that G times x star should be equal to H star, sorry, H, right? So I can write this in the following matrix form. I want to write this in the form of a big matrix times X star gamma star to be equal to minus B H. So what will this matrix be? It is 2A G transpose G 0. And what are the dimensions of this big matrix?
Sorry, n plus d into
N plus D by N plus D. Right. So if this matrix, if this N plus D by N plus D matrix is invertible, then go ahead, just invert the matrix and then you get your solution. But in any case,
sorry, why is it X star and not any X in general? Because we're still not converged on the optimal solution, right?
this is the optimal solution. So X star is, it's only the optimal solution that satisfies these constraints. Yes. Of course, I've ignored one little point, but essentially I've glossed over this, but this problem. So what kind of an optimization problem is this? It's a convex optimization problem because the objective function is quadratic, A is positive definite, so it's a convex, the objective function is convex in X, and the constraints are only linear. All of the equality constraints are, they're affine. So this is a convex optimization problem, and there are no inequality constraints, right? So Slater's condition is automatically satisfied. So this is a convex optimization problem that satisfies strong duality. So if I can solve for the KKT conditions, then I get the solution, right? So the solution must satisfy this system of linear equations, and any solution to this system of linear equations is a solution. Okay. But of course, ultimately it also depends on the rank of this particular matrix, right? And whether this whole system of equations is consistent or not. Because it may so happen that, so firstly, if this is an inconsistent system of linear equations, then there is no point that satisfies, there's no point that is feasible. So you can't end up with a solution at all, right? But as long as this system, this can be satisfied, there will exist at least one solution. All right.
Inconsistency will reflect in the rank of G.
It'll essentially show up in the rank of G, because if you notice, you have this along. So if G is full rank, you can convince yourself that if G is full rank, then this whole matrix is also going to be full rank. All right. Okay.
And what about the case where intuitively the cup defined by your quadratic
Correct.
target function is not intersecting the hyperplane defined by the constraint equation?
What do you mean? So the objective function is well defined over all of Rn or over all of Rd, right? The only problem is this constraint set. If this constraint set is non-empty, then there is a solution. Right. Any questions?
Like, why will it always intersect?
I'm sorry.
Why
Why?
will the gx equal to h always intersect the vowel?
It doesn't have to. So there are two completely different things, right? So gx equal to h defines your constraint set. That's your search space, right? That's your feasibility set. This is the objective function, right? So you don't care about intersections at all. This is a function, whereas the set of all x that satisfies this defines your feasibility set. Okay. Any other questions? Okay, so let's look.
A positive definite matrix always full rank.
Which one?
A positive definite matrix.
Question to you: is a positive definite matrix always full rank? How do you define a positive definite matrix?
V transpose A B is always like that.
Okay, or an equivalent condition greater than 0. Okay, now you tell me whether it is full rank or not. It has to be full rank because all the eigenvalues are greater than 0. Right?
G is equal to H.
Correct.
System of linear distribution, and we have only particular solution if for rank is fixed.
Okay, so again you have to be a little careful here. So typically you choose n to be less than d because you want your constraint set to be something that is non-trivial. Alright, and you can have it to be non-trivial only if there are infinitely many solutions to this system of system of linear equations. And having g, if I also impose the condition that g is full rank, then that can happen only when n is less than d. I have fewer equations than unknowns. If the number of equations is equal to or greater than the number of unknowns and the matrix G is full rank, then I either get 1 point or no points at all, which is not really interesting. Because then if there's only 1 point, then I just have to solve the system of linear equations and declare that to be the solution. But it becomes interesting when G is a fat matrix and therefore I have infinitely many solutions. Now searching over the space of solutions can in principle be difficult. But in this nice case, finding the solution or solving the optimization problem can be done by just solving this system of linear equations, which is not that hard. I mean, compare that to, let's say, running gradient descent, where you may have to just keep running this algorithm for God knows how many iterations. Right? In this special case, this is a nice special case, you get the solution exactly. It's not that you arrive at an approximate solution, you arrive at the exact solution. Another example is something that arises in wireless communications. It's called the. Okay, so let's. Yeah.
Shortcut to finding the inverse of that matrix, just in terms of real.
I'm sorry.
Is there like a shortcut to finding the inverse of that matrix?
I think there is, but is it? I don't have an answer at the. Pretty sure there is. I believe there is, but I can't give you the solution off the top of my head. So, as long as you have this sort of block diagonal structure, you can. There is a simpler expression for the inverse of this, or to solve the system of linear equations. Okay, So I'll motivate this particular problem, but I won't tell you, I won't give you the full details of how you end up with this specific formulation of the problem, because it requires some background in wireless communication or information theory. So if you've taken one of these courses, hopefully you would have seen this problem or will see this problem if you're currently crediting one of these courses. So the problem is the following. I have a transmitter. The goal of the transmitter is to send a message to a receiver. So there's some message, let me call it M, which is a sequence of bits. And the goal is to somehow reconstruct this message to the extent possible. So ideally you want the output of the receiver to be equal to the message that was sent by the transmitter. But unfortunately, this transmitter has to communicate through a noisy medium, and we model this noisy medium as a random process. So it's not possible to recover M exactly, but you can recover M with high probability. Okay. So what does this noisy medium look like? We'll model it in this specific form. So the noisy medium can be represented as a stream of parallel channels. Okay, so there are, let's say, M or N, we use something else. There are P channels. And the transmitter is allowed to use each of these P channels across N time instants. Okay, so we are assuming a discrete time system. So I have these black boxes, which I call channels, and the transmitter can send something in each time instant. It can send something through each of these channels. It can send one symbol in channel 1, some other symbol in channel 2, some other symbol in channel 3, and so on. So this is going to be in each time instant, let's say the tth time instant, it transmits x1 of t in the first channel, x2 of t in the second channel, and xp of t in the pth channel. It's basically just what the symbol that it sends is just a real number. Xi of t is just a real number. So you can send one real number through each of these channels. The receiver gets the real number, which is corrupted by noise. So there is some additive noise, Z1 of t, Z2 of t, Zp of t, and the receiver gets Y1 of t, Y2 of t, Yp of t. So a very simple model of the communication system would be where p is equal to 1. You transmit a real number, the receiver gets the real number plus some noise. I've just generalized this a little bit to say that, well, you don't transmit one real number every time. You can view this as transmitting a real vector. Okay, so in each time instant, the vector y of t is equal to the vector x of t plus z of t, the vector z of t. Okay, is this much okay? Any questions? So this is basically my model for the communication system. And here I'm assuming that each Zi of t is Gaussian with zero mean. Each Gaussian is independent, zero mean, and the ith channel sees a noise variance of sigma I square. So the channels are the p sub channels, they are not identical. They're all independent, but they're not identical. So in the first sub channel, I see noise variance of sigma 1 square. The second sub channel, I see a noise variance of sigma 2 square, and so on and so forth. Okay. The fact that these are non-identical is very important for us. Okay. So that's number one. Number two, the transmitter has to satisfy some sort of a power constraint. Of course, if there were no other constraints, then you could just pump up xi of t. You could transmit a really large value every single time, and then you could transmit almost noiselessly. But I'm not allowed to do that because the transmitter, after all, they're constrained in terms of energy. They have a finite battery or they have some sort of a power source, and you can't use infinite amount of power. So typically, I'm sorry?
What is xi of
So xi of t is what is a real number that is transmitted in the ith channel at the tth time instant.
like how are you converting the binary thing to a real number?
So typically there is something like a digital to analog converter that converts these bits. Of course, there are a lot of other processes that are being done before. So how you get xi of t from m, I'm not specifying yet. Okay, but this describes sort of a general communication setup for this particular channel. Okay, and I'm not going to describe how the bits are going to be converted to real numbers. Okay, but right now I'm just describing the channel itself. The channel is such that you transmit a real number, you get a real number at the output. For example, let's say you use an antenna and you transmit a signal, then you use another antenna to receive this, you get the transmitted signal, which could potentially could suffer attenuation and noise. In this case, we are not assuming that there is any attenuation as such, but there is noise being added. Okay. There are a number of different ways to think of this. Well, one is wireless communication, but you could also think of a setup where maybe these are all, let's say, cables. You have P cables from the transmitter to the receiver, and you're transmitting a signal along each of these cables. So it could be some electrical signal that is being sent through through each, say, coaxial cable.
Type of noise apart from additive noise.
Right now, I'm assuming that it is additive noise. But of course, I mean, in general communication system, you can model it in a much more general way. In fact, for example, if you take a course on information theory, then you will study the case where the output is described by some conditional distribution given the input. So each conditional distribution will define a different channel. But particularly in wireless and wired communication, the most common model to consider is this, where the noise is additive and typically it is Gaussian for various practical reasons. One fundamental reason is because of the central limit theorem, because you have different sources of noise just adding together and averaging out. So in the limit, that will look like a Gaussian. That's one reason. And there are other fundamental reasons. For example, in many ways, the Gaussian noise is kind of the worst case noise subject to a given noise variance. Okay, but yeah, that's again, it's a digression. But right now, this is the model. Okay, you transmit an electrical signal through each of these channels. What you get is the electrical signal corrupted by Gaussian noise. Everybody knows the variance of the noise, but that's about it. And secondly, you also have this total power constraint, So 1 by, suppose that I use the channel for t time instants, then 1 by t summation t equal to 1 to capital T, and summed over all of the sub channels I equal to 1 to p xi square of t. This should be less than or equal to p. So in some sense, this is the total amount of energy that is, or this is the total amount of energy that is being used by the transmitter across the p subchannels and across the t time slots. And therefore the total amount of power that you can use, that you're allowed to use, is t times, the total amount of energy that you're allowed to use is p times capital T. Okay. And the goal is to design a communication system such that in these capital T time slots or capital T channel uses, you can transmit TR number of information bits. So your message, this could be a file, it could be an image, it could be an audio clip, but the total number of bits that this message, the length of the message is capital T times R for some parameter R. Okay? And the goal is to make sure that R is as large as possible, because you want to transmit as many information bits as possible in T time slots. So want R to be as large as possible, but again, you can't make R arbitrarily large, because if you try to transmit too many bits, then after all the channel is noisy, right? So you can't recover exactly what you have transmitted. So you want the probability that m hat is not equal to m to be as small as possible. So one arbitrary demand is that I want this to be, let's say, some constant times e to the minus t times some constant. So in T channel uses, I want the probability that I make a mistake to decay exponentially in T, or something that vanishes as T tends to infinity. So the larger the message I want to transmit, the more reliability I want to get. Seems like a pretty stringent requirement, but in fact it turns out that for very large T you can in fact get this. Okay. Again, I'm not going to go into the details, but this is something that dates back to the 1940s by Claude Shannon. That in fact you can achieve this, you can have a probability of error. So that's this particular probability to be arbitrarily small, but you can't make R to be arbitrarily large. There's a limit to how large R can be, and the maximum R such that probability m hat not equal to m, such that if you want this to go to 0 as t tends to infinity, then this R max, which is also called the capacity of the channel, is given by some quantity But in this specific case, in this specific parallel channel case, this evaluates to half summation I equal to 1 to p log 1 plus pi by sigma I square, where pi is sort of the power that I allocate to the ith channel. Again, since I have a total power constraint, maybe I've sort of overused notation a bit. So let me call K to be the total number of channels. Otherwise it will just become confusing. Okay, so summation I equal to 1 to p, I equal to 1 to k, pi should be less than or equal to the total transmit power. That's the total budget I have. Yeah.
Goal, why is probability and cap not able to less than equal to C e power minus PC? Why does P times?
So that's what I said. So basically what I want is that if I'm allowed to speak for a very long time, then I want my reliability to be as large as possible. One way to try to understand why this might even be possible is, suppose t equal to 1. You're only allowed to transmit one symbol. Okay? You can't make, whatever you do, you can't make the probability of error to be much smaller. Right? Because you transmit x, you receive x plus z, the noise variance, where z is the noise variance. You can't do anything else. And remember that your x has to satisfy a power constraint or an energy constraint. So x is has to be between minus p and plus p. Right? So because this noise variance is something that is non-zero, the probability of error with some little bit of calculation, you can see that it's always lower bounded by some particular quantity. But the beauty of Claude Shannon's result was that if you're allowed to wait for a very long time, that is, you don't just speak for one time instant, but you collect all of the messages you have and then spread it across a long time duration. So the longer the time duration you give, the more messages, the more number of information bits that you are able to transmit. But if you are allowed to do that, then you can make this overall probability of error to be arbitrarily small. As t increases, this quantity goes down, decays very sharply. Right? So the fact that this is even possible is something which is a little bit surprising. But he showed that yes, it is possible to do so. And indeed, there are practical systems today which, for many channels, you can actually get this. You have systems that achieve this. And this particular problem of parallel channels, of course, as I said, one scenario is where you have, let's say, parallel wires running through. But there are many other scenarios as well. Particularly, even our cell phones use an algorithm called OFDM, orthogonal frequency division multiplexing, wherein actually what you have is not this kind of a channel, but with some pre-processing and post-processing, you can reduce it to a system of parallel channels with unequal noise variances. Okay. So again, if you've taken a course on communications or information theory, you may have seen this a little bit, but if not, don't worry about it. Our end goal is anyway to solve this particular optimization problem. Okay. All of this was just a little bit of background to tell you why this problem is interesting or important. Okay, this is something that is of direct relevance, and in fact, even our cell phones use it to some extent today. Okay.
So you're saying this is more practical than seeing the problem as fixing the message length and minimizing the time to transmit it.
So, in general, you will fix the message length,
Yeah.
but typically the length of each block is some large quantity.
The length of each block. That's you're making it variable and you're trying
T.
to max it.
Yeah, so this particular result, it's in the asymptotic limit. You can also give bounds for finite t, but right now I'm only interested in this. Again, I want to solve this specific subproblem. Okay. But in practice, capital T can be anywhere between the range of, let's say, at least a few thousands to, let's say, 10,000 or 100,000.
Okay. So what is the R max equal to C? Is it the same C as the other one?
Which one? Oh, okay. Yeah, again, bad notation. Let me call this C prime, C double prime. This C is different. Okay.
Why did you use C here?
Here, because this is a quantity that is called the capacity of the channel. That's why I use the term C. Okay. Fine. So now hopefully the high level context is kind of motivated enough for you. So right now, again, let's go back to the problem. Effectively, what I have is I have a stream of parallel subchannels. I have a total power constraint, and I know that in each of these subchannels, there's a different level of noise. And your goal is to decide how do I allocate all of this power. I have a total power constraint of P, and I can allocate as much power as I want to each of these specific subchannels. Based on your gut feeling, what would you do?
Divide equally.
Yeah?
Divide equally.
Divide equally. Okay, one strategy is you divide all of this power equally across subchannels. But then now you see that there are some channels where the noise variance is high, some channels where the noise variance is low. And again, remember that the rate at which the goal is to make sure that this quantity is as large as possible. I want to transmit at the maximum rate possible. So now I see that the rate is basically a sum of each of these terms, a sum of rates for each of these subchannels. And if I allocate equal power for each subchannel, I see that if the noise variance is large, then the effective rate is small, right? Because this quantity is inversely, this is a decreasing function of sigma I square. So if I allocate equal power for each subchannel, then over channels which have high noise variance, I'm losing out. I'm unnecessarily wasting power in the channels where there is too much noise. So in a way, it makes more sense to allocate more power to subchannels where noise variance is less, because they're clean, slightly more clean. Over more noisy channels, I shouldn't be wasting too much power. Okay. Any other solutions? Yeah.
We could send some parity bits or checker bits and then perform spectral subtraction on it to check the average power inside each channel, and then arrange them in an increasing order, and whichever has the lowest power gets the highest number of bits allocated to it.
Okay, I'm not sure what you mean. So there's already some parity, whatever. There's some coding going on in the background, which I'm not talking about.
Extra information before we start sending.
So I know exactly how much noise variance there is in each subchannel. Okay.
What if you make PI proportional to sigma square and then normalize it such that the sum equals P?
Okay, so Pi proportional to sigma I square.
So each of the terms in the summation that log, that part will be equal, all of them.
Okay, so basically one suggestion is let's make each pi to be proportional to sigma I square, which means that the kind of solution that you're proposing is if there's more noise variance, then allocate more power. All right? All right?
You can keep some threshold and try to fill it.
If you know the answer, then please don't say anything. Yeah, what else? Surprisingly, no one has come up with the most common answer, which is you take the channel which has the least noise variance and pump in all of the power into it. That's okay. We've abstracted out all of the error, everything out of the picture. Okay. My only goal is to maximize this particular quantity at the moment. How the errors and all are being taken care of is not my concern anymore. There's somebody to design that system. My only goal is to decide how to allocate the power to each subchannel such that this rate or this capacity is maximized. Okay, some things are still a little unclear.
Is it not mandatory to send in each channel?
I don't have to. It's totally up to me. If I want, I can only use one sub-channel. I can remain silent in all of the other sub-channels if I want.
Based on
Yeah.
noise?
Totally up to you.
So you understand R bits at every time.
Again, so all of that was the physical description before, but now I've brought it down to a specific sub-problem. Okay, basically you're transmitting whatever t times Ri bits in each sub-channel, total number of bits in each sub-channel, in the ith sub-channel.
Transmitting.
So effectively the total number of bits to transmit is t times R. Okay, in t channel uses. I'm going to split and somehow encode these t times R bits into different signals and send it across each subchannel. I'm going to receive and I'm going to do some post-processing. I'm not telling you how I'm doing this encoding or how I'm going to do this decoding at the receiver.
What is T, what is R, and what is
So t is the number of time slots that you communicate over.
which means I can send R bits T times.
That's a naive way to do it. But in principle, I get more gains if I code across the t time slots. The effective number of information bits that I'm sending per time slot is R. Okay, but this R could be a quantity less than 1 also. R is not necessarily an integer. It could be 0.12.
What does it denote?
That's the information rate. That is, how many information bits am I transmitting per time slot on average?
What is an information bit? It's a type of
Whatever, yeah, you can think of message. So I'm basically sending a TR length message in T time slots. So suppose I send 1000 bits, a file of length 1000 bits in 2000 time slots.
So R would be one.
Then the rate would be half, R would be half.
So is the T into R constant or
Which, so again I've abstracted out T, R, everything else over here. The quantity is R, right? I'm assuming that T is something that is extremely large. Because if you notice, this T doesn't appear anywhere in this optimization problem. The only parameter that everything except T appears in this optimization problem. the total amount of, you have more energy, yes, but you don't have more power, because power is the energy normalized by the time.
So you can, if it's best channels, then you can send out by increasing the time.
Okay, again, number of time slots is fixed. Okay, that's fixed. I'm not changing anything.
Based on some threshold, we will select only.
So right now, I'm not asking you to come up with a strategy of how to send the information. The only question is, I have an algorithm to send information. I have some. I'm not telling you what the algorithm is, but I have some way of sending the information. The only thing is, how much information or how much power should I assign to each of these subchannels? All right. So basically, my goal right now is to maximize this quantity, half summation I equal to 1 to k log 1 plus pi by sigma I square, subject to the constraint that the total power is less than or equal to p.
Let me consider that till phi sigma, from the mean being 0, from minus phi sigma to phi sigma, 98.9% of the points will lie inside that area region.
Okay.
In Gaussian. So considering the lowest, minus phi sigma to phi sigma.
Okay.
We consider that area for the lowest one, and then correspondingly find the area of all the other Gaussians, and then allocate them power in that.
Okay. Okay.
way.
But why phi sigma to? You mean to say within phi sigma?
It's from minus phi sigma to, I don't exactly remember it, but I think 99% of the points lie between minus phi sigma to phi sigma. So exactly
Okay.
don't remember it.
Okay. So how do you choose pi?
The higher is the area in that very region, the more power is allocated to that region because it has a lesser spread.
So if I have a large sigma I, how should I choose pi?
Pi should be lower than sigma.
Okay. Okay. So anyway, let's try to see what the actual solution is if I solve this optimization problem. So firstly, what kind of an optimization problem is this? What can I say about the objective function? It is? So is this a convex problem? What are the variables? Pi's. So I have k, it's a vector of length of k, right? I have k variables, p1, p2, p3 up to pk, right? My objective function is this particular quantity over here. And what are the constraints? Correct. There's also another constraint which I have not explicitly mentioned. Power should be positive, so pi should be greater than or equal to 0 for all I. Just for convenience, I'll ignore this half from the objective function. It doesn't make a difference except that I'll have an annoying half or 2 in between. Okay, so let's select.
Why won't allocated power proportionally work?
Why won't? Because in some sense, if I allocate power proportional to sigma I square, I'm losing out, I'm wasting power on channels which have too much noise variance. Okay.
But can't you do like the AMGM inequality? This is like a multiplication of 1 plus pi by
Uh,
log of pi times.
okay, but I have 1 plus pi by sigma I square.
Yeah, so 1 plus p1 by sigma 1 square should be equal to 1 plus p2 by sigma 2 square. That would give you the maximum value of the problem.
Okay, but you also have a constraint. So what can potentially happen is, suppose you decide a constant of proportionality, okay, then it's possible that you just may end up using all of the power on the noisiest channel, because you're allocating power that is proportional to the noisy channels. Let's consider an extreme scenario where one of the channels is extremely noisy and all of the other channels are almost clean. Then what would the proportional policy do? It would allocate a huge amount of power to the noisiest channel and allocate very less power to the almost clean channels. But a more sensible thing to do would be you allocate as much power as possible to the clean subchannels and give almost no power to the really noisy subchannel. Right?
But can't we just take the best of the both worlds, like up till a particular value of the noise, we'll keep them proportionate, and after that we'll.
So anyway, let's solve the optimization problem and see what solution we get. Right? Because if I solve this constraint optimization problem, then whatever I get should be optimal.
What about the other thing also, allocating full power to the one with the least variance?
Correct. That's one natural way of thinking about it. But as it turns out, for this objective function, that's not good enough. That's not optimal. Okay. So first, this whole optimization problem is a convex optimization problem. All right. Prove this. So show that this objective function is convex. These constraints are anyway affine, and therefore constraints are convex. So how many Lagrange multipliers do I need in this case?
To get it in the canonical form, do you put it as minimize?
Yeah. I will think of skipping a step, but yeah, let's put it in canonical form first. So we want to minimize minus summation I equal to 1 to k log 1 plus pi by sigma I square, subject to the constraint. Again, I have to bring all of these to standard form. Summation I equal to 1 to k pi minus p should be less than or equal to 0, and minus pi should be less than or equal to 0, I equal to 1, 2, 3 up to k. How many constraints do I have? K plus 1. So I need k plus 1 lambda Lagrange multipliers. So this is going to be a function of p1 through pk, and I'll denote the Lagrange multiplier for the first constraint to be lambda, and for the rest to be lambda 1 up to lambda k. This question? The third constraint, I want pi to be greater than or equal to 0 because it's a power. It has to be non-negative. I've just brought it to standard form by bringing it to the other side, minus pi.
You are saying that in every channel some power should be.
Less than or equal to 0. It can be 0. It can be 0. But it can't go negative.
So this is equal to lambda k plus 1 subscript.
So so this lambda doesn't have a subscript
Oh, okay.
that corresponds to this constraint, whereas each of these have Lagrange multipliers lambda 1 through lambda k. If you want, I'll denote this lambda prime. So this is going to be minus,
Any reason for that choice?
which one?
Like distinguishing it from the rest of the lambdas.
Yeah, this is, it just makes things more convenient. Otherwise, it's going to be a bunch of messy notation. One plus pi by sigma I square plus lambda times summation I equal to 1 through k pi minus p plus summation I equal to 1 through k lambda I times minus p. Is this okay? Let's write down all of the KKT conditions. First, I have primal feasibility. So that's just like restating all of the constraints. So summation I equal to 1 through k, pi should be less than or equal to p, and pi should be greater than or equal to 0 for all I. The second is dual feasibility. Which is that this lambda prime should be greater than or equal to 0 and lambda I should be greater than or equal to 0 for all I. Okay, again, straightforward, nothing interesting here. But we still want to keep this in one side because we'll be using these later on. The next is stationarity, which is that the gradient of the Lagrangian with respect to p should be equal to 0. Right? So what is the partial derivative of this particular quantity with respect to pi? I keep forgetting this, but I should have a star. So what is the partial derivative of the Lagrangian with respect to pi? Assume that the logarithm is with respect to base e. Yeah? 1 by? Are you sure? I'm taking the partial derivative with respect to pi. Right? I'm taking the partial derivative only with respect to pi. So what would be so with respect, if I'm taking the partial derivative of this summation with respect to P1 only, I only get one term, right? So there should also be a negative sign here. Okay, and then I have lambda star correct, lambda I star, right? So this should be equal to 0, correct? If I let's try to rearrange this. So effectively, okay, so first, if I sort of try to simplify this, I get minus 1 by sigma I square plus pi star plus lambda star minus lambda I star. This should be equal to 0, or 1 by sigma I square plus pi star should be equal to lambda star minus lambda I star, or pi should be equal to 1 by lambda star minus lambda I star minus sigma square. Is this okay up to this point? Okay, let's note that down. The fourth condition is complementary slackness. Which is that for all I, lambda I times minus pi should be equal to 0, and lambda star times summation I equal to 1 to k pi star minus 1 should be equal to 0. Or another way of putting that is, for all I, either lambda I star equal to 0 or pi star should be equal to 0. One of them has to be equal to 0. The second is that either lambda star equal to 0 or summation I equal to 1 to k pi star should be equal to p. So the goal is to come up with some choice of pi stars such that all of these conditions are satisfied. So all of these equations are satisfied. So first, let's try to eliminate some of the easy ones. Let's see if lambda star can ever be equal to 0. Suppose that lambda star is equal to 0. All right. So if lambda star is equal to 0, what happens to the choice of pi star over here? what can you say about pi star if lambda star is 0? Yeah?
It will either become negative or undefined.
It'll either be, okay, yeah, if lambda I star is also 0, then it becomes a problem, it's not defined. But if lambda I star is non-zero, then pi star would be negative, which violates the primal feasibility constraints. So lambda star has to be equal to 0. Sorry, lambda star cannot be equal to 0, which implies, so this can't be satisfied, which means that this has to be satisfied. So the sum of the total power should be equal to P. And in a way that makes sense, because if you have a total amount of power and you want to maximize the rate, then there's no point in leaving power unused. You might as well allocate it to some subchannel, because that will be useful. So that's sensible. Now, what about the remaining? Lambda I star equal to 0 or pi star equal to 0? So again, let's go back to pi star. So pi star has to be greater than or equal to 0, and it's equal to 1 by lambda star minus lambda I star minus sigma I square. Okay. So suppose if lambda I star is equal to 0, so if this is equal to 0, then pi star must be equal to 1 by lambda star minus sigma I square. Right? If lambda I star is not equal to 0, then pi star must be equal to 0. Then effectively pi star should be equal to 0, which is 1 by lambda star minus lambda I star minus sigma I square. Or if I try to rearrange, sigma I square should be equal to 1 by lambda star minus lambda I star, or lambda star minus lambda I star should be equal to 1 by sigma I square. Lambda I star should be equal to lambda star minus 1 by sigma I square. But now I also have the dual feasibility constraints to take care of. So lambda I star should be greater than or equal to 0 for all I. So lambda I star not being equal to 0 can only happen if lambda star is greater than or equal to 1 by sigma I square. Right? Or sigma I square is greater than or equal to 1 by lambda star. So what this is basically telling us is that if your noise variance is too large, above a certain threshold, then you should allocate 0 power to that particular subchannel. Right? Which one? It's correct. Even here it is.
But towards the very end, you just got that when you just don't have it,
Yeah.
just make it fully zero, otherwise you utilize. How did we end up with that?
That's why KKT conditions are helpful, because it allow you to, again, it doesn't happen in all problems, but only in certain special problems it becomes much simpler.
If sigma is just slightly above the threshold,
Correct.
then like if it's below the threshold, then we can utilize it.
Then you can utilize
But
it.
we utilize it very less. If it's very low.
Correct.